Okay, now it's time to talk about how to map the features of the Completable Futures framework onto the principles of reactive programming that we talked about before. So the Java Completable Futures features map very nicely onto these principles. Here is some examples, not any means exhaustive, but they will give you an overview of this. So the first thing is responsive. What that means is that we don't want to block the calling thread. When you block the calling thread, oftentimes in historical terms, that was the one that talked to the user interface, or that was the one that talked to the user. And if you blocked the user interface thread, then you would make the system unresponsive because it couldn't handle other GUI events while it was blocked, waiting for some long-running computation to take place. As a general rule, having a lot of blocking in your code will underutilize the processor cores, thereby impeding the inherent parallelism in the system, which is more than just cores, because you can also do I/O in parallel to threads. And it might complicate the program structure if you have to go with a purely event-driven way of writing your software, which is just ugly. So what we have here is we have Completable Futures providing several different types of methods that avoid blocking threads. So one of them are some of the factory methods will spawn things in the background. Actually, all the factory methods spawn computations that run in the background. You have completion stage methods that also will let things run in the background. And there's also something called arbitrary arity methods, which can take groups of completable futures and give you a single completable future that waits for all the other ones to finish. So you don't have to block there either. You can make that asynchronous. So lots and lots and lots of opportunities for asynchrony. Another issue that makes things potentially less responsive is changing threads when you don't need to, unnecessarily moving stuff between threads. And the reason that is a problem is because it incurs too much overhead with respect to various hazards or properties of doing synchronized interactions and concurrent interactions in a multi-core system or a multi-processor system. And this involves synchronization overhead, which is locking overhead, context switching overhead, which is moving entities from one thread to another, stopping one thread, starting another thread, and so on, and memory and cache management. When you move things around between threads or processor cores, you often have to do cache invalidations and cache refreshes, which makes things run slower, even though you don't see it in your code. So moving around between threads can be a problem. And therefore, the fork join pool, and there's a series of methods that are the non-async methods, we'll see what those are, can be used to avoid changing threads if you don't want to. Now, there's also methods, these async methods let you change threads, but you don't have to do it. You can make the decision about whether you change threads or not. Sometimes it's a win, sometimes it's not a win. So that was responsive. So we can avoid blocking user code, we can avoid changing threads. Another thing that you get to map stuff from completable futures onto these principles is resilience. So how do we make programs more resilient to failure? And the way we do this is by exception methods. So there's a bunch of methods that are part of the completable futures framework that catch exceptions that occur in asynchronous threading contexts. And when we get to that part of the course, I'll go into this in a lot more detail. You really need to have special features for handling exceptions asynchronously because the whole idea is to start an operation and not block the caller. But traditional Java exception handling is synchronous. You have a try-catch block, you invoke a method, you block till you're done, you either get the result back or an exception is thrown. With asynchronous programming, you start something, you, the caller, go off and do something else, the thing runs in the background asynchronously, and when something goes wrong, the caller may not be in any state or any context to do anything about it. So we have to make sure we handle the exceptions in the right context. And these exception methods do that. And basically what they help us do is they decouple the error processing from normal operations. Notice, by the way, that completable futures in Java, like parallel streams, are localized to a single process, not a cluster. So you can do cluster programming, but it's not going to be done with this. You could use other programming models like Hadoop or Spring or other things that could run in a cluster. Elasticity, of course, is a big deal. That's one of the reasons why people often choose to incur the learning curve to come up to speed on how to do reactive programming, is because they want to make things run faster or run more scalably. And what you get with the completable futures framework is ways to run computations asynchronously in a pool of threads that are mapped atop a set of cores. And as I mentioned before, there's some options here. You can either use the common fork join pool, which is what's the default if you don't do anything else to the contrary, or you can provide a user-defined or a predefined thread pool. And then the fourth mapping is message-driven. And this is not quite as obvious, because when you look at the API for completable futures, you'll see that by and large, it's a bunch of method calls. I mean, pretty much everything is a method call, which doesn't look message-driven at some level. However, if you peek into the implementation, which we will do, of the completable futures framework, you'll see that under the hood, there's messages being created all over the place internally, and those messages are being queued up in the various double-ended queues inside the common fork join pool, or if you use the common fork join pool, or even if you don't use the common fork join pool, there'll be queuing of messages typically somewhere. And so there's message passing taking place between threads and between different elements in the system. It's just that there's a facade that encapsulates that in a nice method-oriented veneer. And of course, the reason for doing some of this stuff, especially the message passing in the fork join pool, is to support work scaling. So that's the end of the overview that maps completable future features onto reactive programming principles.